These are the frequently asked questions for pre-calculus for section 2-1, day 3. We have some word problems here that we need to deal with. And those word problems are starting with number 54. It says, among all the rectangles whose perimeters are 100 feet, find the dimensions of one with maximum area. So the information I have is the perimeter is 100 feet and that we're talking about a rectangle. And I realize I don't know the length or the width, but I'm going to have one of those be my unknown. And then I start thinking, okay, well, if those are x and I have 100 for all the way around, I would have to subtract the 2x to figure out what's left for these two sides. And since it's a rectangle, those two are both going to be the same. So that means I can split that equally between the two of them. And that would give me 50 minus x as the other dimension. And then I start thinking about maximum area, and area is length times width. So x times 50 minus x, and then that will give me 50x minus x squared, which is going to be negative x squared plus 50x. And if I want the maximum area, what I'm really looking for here is the vertex. So by hand, we would do x equals negative b, so negative 50, over 2 times a, which is negative 1, and that would give me 25 feet. And now if I want the other dimension, I can go back to my formula and see that the other dimension is 50 minus my x value. Well, my x value was 25, so 50 minus 25 is going to be 25. And as we often see, it's in fact a square that would give us the maximum area for that rectangle. It's a square of 25 by 25 feet. Number 55 says, the per unit price in dollars of a popular toy when X units, and this is important, in thousands are produced is modeled by the function that the price is 12 minus 0.025x. The revenue in thousands of dollars is the product of the price per unit and the number of units in thousands produced. And I just have a sneaking suspicion that that was the piece that you missed when you were doing this. So thousands of dollars in thousands produced is revenue equals XP, which is X times the quantity 12 minus 0.025X. And for A, it says state the dimensions of a viewing window that shows the graph of the revenue model for producing 0 to 100,000 units. So if I want to do that, I need to think, all right, well, my X here. My X was for what? And my X had to deal with this function right here, where it was units in thousands that are produced. So when I set up my window, I want to think about the fact that I'm going to have 0 as my startup, and then I need to figure out what I want to use for my value as a cutoff on the high end. And we can always graph it and take a look at that piece later, but we need to remember that that's in thousands of units. And then once we have those numbers, once we know what we want to look at, we can put a 0 back into this formula and see what we get. And 12 minus 0 is 12, so our output would be 12 from that one. And the way to kind of figure out what it is we really should have for the other end would be to go ahead and look at B and see that they're going to ask us how many units should be produced if the total revenue is to be $1 million. However, if we go back, we have to remember that these numbers were in thousands. So that actually would be a Y value of 1,000. So we might want to make this 1,250, something along those lines, so that we're sure that we're going to see that. And we could always work backwards and figure out what the other end of that is. But really, what they wanted us to do with this was get it into the calculator and then play around with that window and see what we can get. So we go into y equals, and we punch in x parentheses 12 minus 0.025 x parentheses, and put it in exactly as it is. And then for our window, remember we were going to start with 0 and we were going to look at thousands of those units that we have there for X. So maybe I'll just stick with 25,000. That's what it happened to be at already. And my Y's going from 0 to, remember we said maybe we'll do 1,250 to be sure that we can see it. And we do see some growth there, but we realize if we're looking for maximums at all in any of this, we're probably not going to see it in this window. So we need many, many more X's. So let's go back into that window and make a few changes and try 0 to 500 for our X values. And we do get a better view of what's going on, but we still don't see the top. So one more time, let's get the top of this. 1250 was not high enough, so maybe 2,000. If we want to see the whole graph, we could do that. Now, what they had in the book was a smaller viewing window, but like I said, it depends on what you want to find, and we can now see the whole thing, so that would be the point of this. So if we go back and look at our window, we use 0 to 500 and 0 to 2,000. Now, this is just a matter of taste. You know, what is it that you like to see? And I wanted to see the whole graph. So A will be different depending on what it is you wanted to see. It could be a smaller window if you were just really concerned about answering part B. So state the dimensions of a viewing window that shows a graph of the revenue model for producing 0 to 100,000 units. Well, if we're just going to do the 0 to 100,000 units, then we could have stopped right here at 100,000 units. But what we need to do is figure out, or actually that would be the top one here. So that would do it as well, but we wouldn't have seen the very top of that graph. So to meet their specs, you'd have to have 0 to 100 in the first portion of this, the domain, the X's. But kind of up to us for that second one. They had 0 to 1,000, but you're not going to see the top of that curve, top of that quadratic if you do that. So maybe 2,000 would be a little bit better. And then B says, how many units should be produced if the total revenue is to be $1 million? And this is what I had mentioned earlier. Because that's in thousands, what we really want to know is, and we'll just do this on the calculator, what is y sub 2 equal to? You have to take 3 of those zeros off because this was in thousands. When will that be equal to 1,000? And we could just use the calculator for this by going into y sub 2 and setting that equal to 1,000 and graphing. And then going ahead and finding the intersection. So second, trace number 5, and there'll be 2 intersections here. And I'm just trying to get Blinky into position where he'll realize I want this intersection on the left-hand side. So we're saying when X is 107,335.01, because remember that was in thousands of units, that this is going to happen. Get that so I can read it. 107,335. And we did have another one, but which one they're going to produce at is always up to the company. In good times, they might produce at the higher end, which is the other one over here. But in times of poor economics, they will produce at the lower one, which is the one that we just had over there of 107,000 and change. So our intersection there is 375,000. how many units should be produced if the total revenue is to be $1 million? Well, either 107,335 units in good times, or I'm sorry, in bad times, and in good times we would use 375,000 units. All right, number 61. Number 61 uses our vertical free fall motion formula, and this is talking about a ballpark. And it says that as a promotion for the Houston Astros downtown ballpark, a competition is held to see who can throw a baseball the highest from the front row of the upper deck of seats 83 feet. So I know this is in feet, which tells me I need to use 32 feet per second squared for gravity. The winner throws the ball with an initial vertical velocity, this is V sub naught, of 92 square feet. Now, what they gave us here, the 83 feet above field level, that's S sub naught. So that means we have S of t equals negative 1/2 of 32 feet per second squared, because this was given to us in feet, plus our V sub naught was 92 t plus 83. And we can pretty that up a little bit. I mean, we definitely can figure out a negative 1/2 of 32, negative 16t squared plus 92t plus 83. And what they want for A is find the maximum height of the baseball. We could punch that in and find the maximum, but we can also do it by hand using negative b over 2a. And that would give us negative 92 over 2 times negative 16, which is 2.875. So that's going to be the x-coordinate of our vertex, which is really h. And then if we put a 2.875 back into our formula up here, that will give us k. And that comes out to 215.25. So find the maximum height of the baseball. That's the second piece that we just found. The maximum height is 215.25 feet above the field. Now I didn't punch that one in again. Probably should do that rather than trust the numbers that they had here, just because they usually round to 2 decimal places. So negative 16 times 2.875 squared plus 92 times 2.875 plus 83. And it is exactly 215.25 feet. So there's the maximum height above the field. And then B says, how much time is the ball in the air? Well, remember when we did this in class, what we said was, you can think of this as your graphing window, and then what you're really finding is the zero, finding the zero there. So it's up to you how you want to do that. It's kind of big numbers. I probably would just grab the graphing calculator and punch it in and find the zero. So let's go back to the calculator. And we had negative 16 x squared, and then we needed that plus 92 x plus 83. And our window here probably doesn't have to be as large. If this is a ball that's being thrown, and this was in feet, let's try 100 feet, just to see. Okay, well, it went much higher than it did wider. So we'll change that window. We don't need so many x's, but we do need a bigger y max. And since we need the zero, even though I can't see the top of this, I wouldn't have to change this. The calculator can find the 0 without it, but it would kind of drive me nuts not to. So, uh-oh, got stuck again. There we go. Now, to find that 0, I know in the past some of you don't like that you can't see where the x-axis is, so you might want to actually change your y-min here to something like -5, so you'll be certain that you're seeing that axis. Because like I said, I know in the past some of you have said you didn't like that we didn't get to see that. So second trace, number 2, and Blinky needs to be to the left of the x-axis, so he needs to be above it. There we go. So Blinky's above it, and I press enter. Then I use my right arrow to go below the x-axis, press enter, and enter through guess. And so our 0 is 6.543. 6.543 seconds. And then C says determine its vertical velocity when it hits the ground. Well, that's what this formula is for. And that would be V of t. So now we're going to use that formula along with the 0 of 6.543 seconds. So our new formula would be gravity, -32, and then x, which for us is 6.543, and our initial velocity of 92. And we'll punch that one in and see what we get. So -32 times 6.543 plus 92 comes out to a -117.376. So the downward velocity of the ball is 117.376, and this was in feet per second. Again, that's why we had to use the gravity of 32 feet per second. All right, same type of problem for number 63. At the Bakersville 4th of July celebration, fireworks are shot by remote control into the air from a pit that is S sub naught, 10 feet below the Earth's surface, and that's going to be a -10 because it's 10 feet below the Earth's surface. Find an equation that models the height of an aerial bomb t seconds after it is shot upward with an initial velocity of 80 feet per second. So we're in feet again, and then it says to graph it. So for A, we're going to go ahead and put these back into the formula, and because gravity stayed the same, we're going to have half of our -half of our 32, so -16 t squared, and our initial velocity here they said was 80. And then again, since it's under the ground, we have to put a -10. That's probably where anybody messed up, if they did mess up. So graphing this, we know we're going to see a quadratic. And their suggested window was that your x's be from 0 to 5, and your y's be from -10 to 100. But again, you know, that may change depending on the view that you believe is going to give you everything that you need to see. So we have that, and then it says what is the maximum height above ground level that the aerial bomb will reach, and how many seconds will it take it to reach that height. Those are the coordinates of the maximum. So we need to get this into the calculator and let the calculator do the work. We still have our -16 from the last problem, -16 t squared or x squared, but now we want to put an 80 in this position and a -10 in the C position. So let's see here. I think we'll go ahead and set the window for their recommendation. which was 0 to 5. And then they had the y's from -10 to 100. And we hit graph. So this is what I was talking about earlier with the other graph. If you want to see everything that you need for the graph, this is the view you want. You can see both of the x-intercepts here and the maximum. And we're interested in the maximum. So number 4. And let's get Blinky on the left-hand side of the hill going down and press enter. Uh-oh, better redo that. Second, trace number 4. There we go. Enter. Arrow to the right until Blinky starts coming down. Enter. Enter through guess. And there it is. A maximum of, well, if we round, 2.50 and 90. So now we go ahead and say, well, what does this mean? The maximum height is 90 feet after 2.50 seconds. So some really, really good physics. I mean, that's what we're doing here. This is a good physics problem. All right. Next up, number 71 says the initial value of f of x equals 3x squared plus 2x minus 3 is 0. Justify your answer. No, it's not. If you put 0 into this function, you get 3 times 0 squared, that's 0, plus 2 times 0, which is 0, minus 3. F of 0 is -3. And that, again, is your y-intercept. Your initial value is your y-intercept. So f of 0 equals -3. So the initial value is not 0. That's false. The initial value is -3. 72 says the graph of the function f of x equals x squared plus x plus 1 has no x-intercepts, and justify your answer. Well, if I can figure out where the vertex is, then I can answer this question, because I know this is an up opening parabola because a is a +1. If the vertex is above the x-axis, then this is not going to have any x-intercepts. So I would move the 1 out of the way. I already have a 1 for my a value, so I don't need to do any division. And then b over 2 squared will be 1/2 squared, which is 1/4 to complete the square. So over here we have -1 plus 1/4 is going to be a -3/4. On this side we now have that perfect square of x plus 1/2 squared, because that was our b over 2. And then we go ahead and add the 3/4 to both sides. So our vertex is at -1/2, 3/4. Notice the y value is at 3/4, and that is above the x-axis. So we would say our vertex is above the x-axis, and our parabola opens up. So there will not be any x-intercepts. So it said the graph of the function f of x equals x squared minus x plus 1 has no x-intercepts. That is true. And there were different ways to go after this. You know, you could use the discriminant to see that those would not be real solutions as well. But another good practice problem for completing the square.